Hello everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying relations lecture 1. Basically this is the only lecture for relations and after that we'll be starting with functions. So let's get directly started with the discussion. So this is QOD 9 of question of the day series. Just take the screenshot for this. Now let us start with the cardinal number of sets. Cardinal number is nothing but the number of elements in a particular set. Now we'll be looking at two cases. The first one is A union B. The second one is A union B union C. So let's look at A union B first. So before starting that, we already know that in a particular set, let's say we have a set A called 1, 2, 3, 4, 5. We know that we cannot repeat any number, any element over here, right? We cannot write it like 1, 2, 3, 4, 4, 5, 5. We cannot write it like this, right? We have to write it like this only. Every element is presented only one time. Now why I'm saying that, so let's look at A union B first. This is A, this is B. Now we know that this region contains elements which are both common to A and B, right? And to present it in a set format, what I'll have to do, we'll have to write them just once. We cannot write them twice if we have to present A union B. So let us understand this with the help of dot method. Now this particular set A has two regions. One region is this, one region is this. This region has only elements which belong to only A and there is nothing in common between A and B. And this region has only elements which are common in both A and B, right? So I'll be presenting both the zones with the help of a dot. Same with B, right? Now if I write just NA NB, NA means total elements in A, NB means total elements in B. If I write this, in that case, what will happen? NA is this plus this, NB is this plus this. So if we have to write the union, we cannot write it like this, right? Because we just want dot once. We cannot repeat this particular zone twice. As we know the property of sets, we cannot have same elements twice in a particular set. So that's why we have to remove this element. For that we have subtracted n A intersection B, right? That's why this formula came. Got the point? Now let's look at for A union B union C. We'll use the same method. Now I can divide my entire set, any one set, in 4 regions. This particular region where only singular elements are there, there is nothing in common between A and B, A and C, or A, B, C. So just single elements over here. Now over here, elements common only between A and B. Here elements common between A, B, and C. And here elements common between A and C only, right? Similarly, I can write it for, if I'm writing NA plus NB plus NC, then for NA, I have made these 4 dots. For NB, what will happen? This one, this one, this one, and this one, right? For NC, similarly, this one, this one, this one, and this one. Now we know that to satisfy the property of sets, that common elements shouldn't be repeated in a particular set. What we'll have to do, we'll have to remove the extra dots, right? Now this region, this particular region, if I mark it like this is A intersection B. If I remove one dot from here and one dot from here, then I'll be removing one time A intersection B, right? So I have removed this and this. So minus N A intersection B. Similarly, I'll remove one this and this. That will give me N A intersection C. And similarly, what I have done, I have removed this and this. Minus N B intersection C. But in this process, we have got one dot over here, one dot over here. Everywhere we have got one dot. But in the common region, the total common region, we haven't got any dot. So to put an extra dot over here, what we'll do, we'll add NA intersection B intersection C. So now we have got one dot over here. Basically, none of the elements is being repeated in this entire set. So this is our formula for A union B union C. For N, A union B union C, this is the formula. NA plus NB plus NC minus A intersection B minus NA intersection C minus NB intersection C plus NA intersection B intersection C. Got the point? Now, based on these two derivations and these two cases, we can solve all the PGDBA problems related to these kind of problems. Now, let's talk about Cartesian product now. Cartesian product or cross product means the product of two non-empty sets in an ordered way. What does that mean? Let's say we have one set as 1, 2, 3. Let's say we have B as A, B. So to write A cross B or A cross B, we'll take first element from A and we'll take second element from B. And we'll make this pair. So this pair is just one element of A cross B. Similarly, we'll have to make other pairs as well. 1, V, 2, A, 2, B, and so on. All the possible pairs, right? So we can clearly see that number of elements in A cross B will be number of elements in A into number of elements in B. Because for every element of A, we are taking pairs with every element of B. So in that case, total number of cases or total number of elements in A cross B will be NA into NB. That's what we have written over here. Now let's talk about B cross A. We initially talked about A cross B. Now so we had A as 1, 2, 3 and B as A, B, right? So B cross A is A, 1, A, 2, A, 3, B, 1, B, 2, B, 3. Now we can clearly see that A cross B is not equals to B cross A, right? Unless both A and B are same sets, equal sets. If A and B are equal sets, in that case A cross B equals to B cross A. In any other case, A cross B and B cross A are not same. We can clearly see that because of the ordered pairing, because these are ordered pairs. If they would have been unordered pairs, things might have been different. But in case these are ordered pairs, we have defined Cartesian product or cross product like that only. That case, A cross B is not equals to B cross A. Now that Cartesian product builds the foundation for the relations. So what is a relation? Relation is nothing but a subset of Cartesian product. So we got A as 1, 2, 3 and B as A, B. Now we got A cross B as 1, A, 2, A, 3, A, 1, B, and so on, right? Now if I write R as 1, A and 1, B, and let's say 2, B as well. So this is a subset of A cross B, right? Only 3 elements and all these 3 elements are present in A cross B. So this is a subset. Now this is called a relation. This is just one relation. Now how many total relations we can get? We know the formula from set theory that if we have n elements over here, n elements over here, then 2 raised power n is the total number of subsets. So here 6 elements are there. So we'll have 64 number of subsets, 64 number of relations basically. So let's break it down further. In A cross B, let's say NA equals to A and NB equals to B. Number of elements in A set is A, number of elements in B set is B. In that case, what will happen? Number of elements in A cross B equals to AB or A dot B, right? Now these are the number of elements. And now we have to find the subsets for finding out the number of relations. So that will be 2 raised power AB, right? Because AB is the number of elements in cross product. So that's why if we are given a set A and set B, then 2 raised power A, 2 raised power AB is the number of elements, or uh, then 2 raised power AB is the number of relations or subsets of A cross B. So these are the points which I have explained in this slide. Now, initially what happened is we used Venn diagrams to represent or to visually represent, sorry, sorry. We used Venn diagrams to visually represent the sets. Now, for visually representing the relations, we'll be using arrow diagrams. Now, let's consider one relation. So set A is A comma B comma C here, and set B equals to 1 comma 2 comma 3. So this is our set A, this is our set B, right? Now let's define one relation. That would be, let's say A comma 1, B comma 1, and let's say C comma 2. So we have defined this relation over here. Now what we'll do to represent this relation, what I'll do, I'll draw one arrow from A to 1. I'll draw one arrow from B to 1, and I'll draw one arrow from C to 2. So basically set A, from set A we are drawing arrow towards set B. So basically if a function, if a relation is being defined from A to B, in that case we'll be drawing arrow from A to B. Now we can see that all these three elements have been mapped. We say this is mapping. All these three elements have been mapped. So one is called image of A. One is also called image of B. Two is called image of C. There is no name for three. Only those which are being mapped are called image of the respective elements. So one is image of A, one is also image of B, two is image of C. Similarly, A is pre-image of 1, B is pre-image of 1, C is pre-image of 2. So this is called pre-image. Right. Now let's talk about domain, codomain, and range. We've got this as set A, this is set B, and let's say we have defined this relation B1, B2, and C2. All right. Now we see that there is no mapping for A and 3, right? But we have to mention all these when we are drawing the arrow diagram. We have to mention all the elements which are present in set A and set B. Now the definition of domain says all those elements which are being mapped. So B, C, D are being mapped. All those elements of A which are being mapped. So B, C, D are the elements of A which are being mapped. So this is called domain. So domain is B, C, and D, right? Similarly for range, those elements which are being mapped, basically the arrow which is pointing towards them. So here 1 and 2 is there, 3 is not there. So range is 1 comma 2, right? Now for codomain is simple. It's the set B. So codomain equals to set B, which is 1 comma 2 comma 3. In any case, codomain is set B, and you got the definition of domain and range. Now let's talk about identity relations. Identity relations are nothing but those relations which are related to itself. So let's say we have set A that is equals to 1 comma 2 comma 3. So identity relation will be this is A, this is A, 1 2 3 1 2 3, sorry, 3 over here. So 1 is related to 1, 2 is related to 2, 3 is related to 3. So this is the identity relation. Now we know that relations are nothing but subsets of a cross product, or they are basically sets. So we have same kind of forms for their representation, that is roster form, set builder form. These are the two forms we have used to represent sets earlier in the set theory, right? And relations are nothing but subsets, basically sets. So that's why we'll be using only these two formats for representing them. Now let's talk about types of relations. So this is the most important topic of the chapter relations, because most of the questions in PGDBA are being asked from this only. So let's talk about symmetric first. So symmetric is just as the name suggests, if a comma b is present in R, then b comma a also should be present in R. So let's take an example. Let's say we have this relation where 1 comma 2 is there and 2 comma 1 is there. So if 1 comma 2, basically if a comma b is there, then b comma a should be there. If that is the case, in that case this is a symmetric relation. And let's say we have one more element over here. Let's say we have 2 comma 3, but we don't have a 3 comma 2 over here. In that case, this won't be a symmetric relation. Now talking about reflexive. Reflexive means if a comma b is there, then a comma a should also be there. That is also very simple and intuitive. So let's say again we have 1 comma 2 over here, 1 comma 1 over here, and let's say 2 comma 2 over here. Now you can see that if this is, we'll have to check for every element over here. If this is a comma b, in that case we have a comma a over here. Now again we'll check for this. If this is a comma b, again we have a comma a over here. Same for this one. So this is a reflexive. Let's say if we have 3 comma 2 over here. In that case we don't have a 3 comma 3, right? We have to repeat we have to repeat the element, the first element. So we don't have a 3 comma 3 over here. In that case this particular set won't be a reflexive relation. Now let's talk about transitive. This is the trickiest one. So let's move to the next page. Okay, I'll try to explain it over here only. Now let's look at an example. Let's say we have an relation R. So 1 comma 2 is there, 2 comma 3 is there. So by the definition of transitive, what should be there? 1 comma 3 should be there. If it is there, then it's a transitive relation. Otherwise, it's not. Now the trick comes over here. Let's say we have this relation 1 comma 2 and 1 comma 3. Now tell me if this is a transitive relation or not. Actually, this is a transitive relation because the initial condition is not being satisfied. We have to look for a comma c only when this initial condition is true. Otherwise, we have to assume that this is a transitive relation because the initial condition is not getting true, right? If we just have a comma b over here, we have another a comma b over here. We don't have v comma c over here. When we don't even have v comma c, then how can we expect a comma c in this relation? So that's why this is transitive automatically, right? So this is a trick question usually asked in PGDBA or many other examinations. Now the fourth one is equivalence relation. Equivalence relation is nothing but if a particular relation is symmetric, reflexive, and transitive all at the same time, then in that case, that particular relation is called equivalence relation. That is a very simple definition. The most trickiest one is transitive. Now let's look at this illustration. Now one more thing I have to add is when we are checking all these relations, we have to check every pair, every pair. Now let's look at this illustration. We have been given R as 2 comma 3, 2 comma 4, 3 comma 4, 4 comma 5, 4 comma 4, and 5 comma 5. Now let's look at first if it is symmetric or not. So we have 2 comma 3 over here, but we don't have 3 comma 2 over here. So this is clearly not symmetric. This is not symmetric. Now let's look at if it is reflexive or not. Now we have 2 comma 3 over here. So we should have 2 comma 2. Again, we don't have 2 comma 2 over here. So this is not reflexive. Now let's look at transitive case. So we have 2 comma 3. Now what I'll do, I'll try to find pairs starting from 3. So we have 3 comma 4 over here. Only we have just one pair. So if 2 comma 3 is there, 3 comma 4 is there. So we should have 2 comma 4, which is there, right? Now let's look at next element, 2 comma 4. Now we'll look at the element starting from 4. So we have two elements over here. One is 4 comma 5. The other one is 4 comma 4. Now in this case, many people make mistakes. What they do, they'll just check with the one pair. We have to check with all conditions. We have to check with this pair and we have to check with this pair also. So for this pair, what we'll get, we should have 2 comma 5, and with this pair we should have 2 comma 4. Now if you would have checked with just this pair, 2 comma 4 is there, but we don't have 2 comma 5. If you wouldn't have checked with this pair, you would have missed this case. So this is also not transitive because we have 2 comma 4, we have 4 comma 5, but we don't have 2 comma 5, right? Now let's look at this example. So this is 3 comma 4 and 5 comma 6. We can clearly see that this is not symmetric, this is not reflexive, because for 3 comma 4 we don't have a 4 comma 3, and for 3 comma 4 we don't have a 3 comma 3. So clearly not symmetric, not reflexive. Now comes the trickier part, that is transitive. So we have this one pair a comma b, which is 3 comma 4, but we don't have something starting from 4, right? We don't have 4 comma 5 or 4 comma 6. We don't really have that. So in that case, that condition is being negated. That is why it is automatically transitive, because we don't have a pair of b comma c to make it a comma c, right? Now let's look at this example. R is x comma y, x is sister of y. What type of relation is this? So we'll first check for symmetric. So we have given as x is sister of y. For symmetric condition, what we'll do, we'll replace it x with y and y with x. Y is sister of x. This is a little tricky because if x is sister of y, then y can either be a boy or a girl, right? X is female, but y can be a male or a boy. So y is sister of x. It's not really possible. It might or might not be possible actually. So basically, if y is a boy, then he cannot be sister of x, right? So that is why it's not symmetric. It's not satisfying every case. It's not symmetric. Now let's talk about reflexive. In case of reflexive, we'll replace y with x. X is sister of x, which is again not true. One cannot be sister of herself, right? Uh, a person can be sister of someone else, but a person cannot be sister of herself. So that's why it's also not true. Now let's talk about transitive. So if x is sister of y and y is sister of z, then our transitive condition says x should be a sister of z. Now we know that x is female because x is sister. Now we also know that y is also sister, so y is also female. So z can be anyone. It can be a boy or it can be a girl. It can be male or female. But x is female. So if we write x is sister of z, that is true because x is sister of y is sister of z. In that case, we can say that x is sister of z as well, right? So it is transitive. Now take this question as a homework question. R is x comma y, x is divisible by y. What type of relation is this? Take this question as homework. Now let us talk about inverse of a relation. We have been given a as a comma b comma c comma d, b as 1 2 3. This is our set a, this is our set b. Now we have defined one relation, a comma 1, b comma 2, c comma 3. Now for calculating the inverse, for finding out the inverse, we just reverse the elements. When we are defining normal relation, we are defining from a to b. In case of inverse, we are defining from b to a. So that is why we have reversed the order, right? Because when we write the cross product, when defining from relation a to b, we write first element from a, from the one which is being defined, to which is being defined, we write the second element. Similarly for b to a, when we are defining a relation from b to a, in that case we'll write the first element from b and then second element from a, right? So that is why this inverse, a 1 comma a 2 comma b 3 comma c, and our arrows also will change. So this is actually the inverse. This is b, this is a. Now we are defining from b to a. 1 comma a, this is being defined. 2 comma b, this is defined, and 3 comma c. Now initially in this relation, in this R relation, we had defined 1 comma a comma 1, b comma 2, and c comma 3. Now we see that here domain is a comma b comma c because only these three are being mapped. Similarly, our range is 1 comma 2 comma 3, and our codomain equals to 1 comma 2 comma 3. Now in case of inverse, domain equals to 1 comma 2 comma 3, range equals to a comma b comma c, sorry, and codomain equals to a comma b comma c comma d. Now we see that domain and range get swapped. We cannot comment on codomain, but we can definitely say that a domain and range get swapped. In case of this relation, domain was ABC, range was 1 to 3. In this case, domain is 1 to 3, range is ABC. So this is valid for even functions. We'll study about that later. But this is true for every relation. Domain and range get swapped, and CD you can just find the other set, the one which is being defined. So this is it for today's lecture, and I hope you are all enjoying this mathematics series for PGDBA 2023. And from tomorrow onwards, we'll be starting with functions. And the quizzes, notes, examples, reading material, and all that stuff has been uploaded in the Prep Master portal. You can just log into your Prep Master portal and watch that content. So let's meet tomorrow. Thanks for watching.